It's incredible how much technology powers our lives these days, isn't it?
Oh, totally.
But if you're like me, sometimes trying to understand the nuts and bolts of it all, it feels like trying to catch smoke. You get little bits and pieces, but the core understanding can be, well, elusive.
Yeah, I get that.
Well, that's exactly what we're doing today, a deep dive to really extract the crucial insights from some truly foundational work.
That's right. Today, we're focusing on the mathematical thinking that really underpins computer science. And to help us navigate this, we're looking at the groundbreaking work of Leslie Lamport, drawing in part from a fascinating interview he did with Quantum Magazine on YouTube.
What's so compelling about Lamport's story is that he approached computer science with a mathematician's mindset, fundamentally shaping a field that, as he himself has pointed out, was still, really in its infancy when he began.
Definitely.
Our mission today is to understand how that mathematical perspective revolutionized the way we think about and, well, build the computer systems we all rely on.
And before we dive into Lamport's insights, we want to acknowledge the support of Stonefly.com. They're a solution company in data management.
Right.
They've been providing crucial data management solutions to customers for, wow, over 2 decades now.
Okay, so let's start at the beginning. Leslie Lamport's initial foray into this world was as a programmer. And it's interesting that he didn't immediately see himself as a computer scientist.
Exactly. His background was firmly rooted in mathematics, and that mathematical training really influenced how he looked at computing problems. He's mentioned that for a mathematician, when you come up with an algorithm, your first instinct is to think about, well, how you would prove that it actually works correctly.
Which is a really different way of thinking about it, isn't it?
Yeah.
He famously said, an algorithm without a proof is a conjecture, it's not a theorem.
Mm-hmm.
For someone used to just making things work through code, what's the fundamental shift in their approach when they start thinking about proving correctness mathematically?
It's a move from focusing on implementation details, like the actual lines of code, to establishing the underlying logical validity. A proof provides a guarantee that the algorithm will always behave as intended. Regardless of the specific hardware or software environment, it's about building absolute certainty into the foundation.
Okay.
And this highlights a key distinction Lamport made: the difference between the intellectual work of designing the algorithm, the programming, in a deeper sense, versus simply writing the code. He likened coding to the mechanical act of typing versus the creative process of writing.
Ah, that analogy really hits home. Typing versus writing.
Yeah.
Yeah. So before even touching a line of code, he believed in mathematically defining what the program was supposed to achieve. He even created a language called T+, for formally writing down these ideas before coding. It sounds incredibly rigorous, but he also noted that it could be a challenge to get engineers, often focused on deadlines and practical implementation, to adopt this more theoretical approach. Why do you think that resistance exists? Is it purely about time constraints? Or is there maybe a more fundamental difference in how mathematicians and engineers often approach problem solving?
I think it's a combination of factors. There's definitely the time pressure in real-world engineering. Writing formal specifications and proofs takes time and effort up front.
Yeah, makes sense.
But there's also, I think, a difference in mindset. Engineers are often driven by immediate, tangible results. Does the code run? Does it solve the problem now?
Right, the immediate fix.
Exactly. Mathematicians, on the other hand, are trained to seek universal truths and guarantees. The value of a formal proof might not be immediately obvious when you're facing a looming deadline, even though it can save significant time and resources in the long run by preventing subtle but critical errors. And for you, the listener, understanding this emphasis on rigorous proof provides a stronger foundation. It helps you grasp the underlying logic of complex systems without feeling, lost in the weeds of implementation details.
That's a good point, like a building on solid rock instead of sand.
Precisely. And companies like Stonefly.com, our sponsor, they understand the importance of that robust underlying architecture in their advanced data management solutions. They're all about that reliability.
So from this mathematician's perspective on early programming, how did Lamport find his way into the seemingly different world of distributed systems? That seems like a jump.
It was quite by chance, actually. He received what's called a preprint paper from Robert Thomas and Paul Johnson.
A preprint, like an early draft.
Exactly. For someone unfamiliar, a preprint paper is essentially a draft of research that's circulated before formal peer review and publication. This particular paper outlined an algorithm for distributed databases.
Okay, distributed databases.
Mm-hmm.
Data spread out everywhere.
Right. And the fundamental challenge with distributed databases where you have data spread across multiple computers is ensuring that all those computers maintain a consistent view of the data. You don't want one server saying your bank balance is one amount, while another says it's something completely different.
Exactly. That would be chaos. So what did this paper propose, and how did Lamport's mathematical mind react to it?
Well, the specifics of their algorithm aren't super crucial for our deep dive, but what's fascinating is Lamport's realization. He saw that it inadvertently violated a core principle he understood deeply from his study of special relativity, causality.
Wait, special relativity.
Like Einstein.
Yeah, exactly. Special relativity tells us that simultaneity is relative. What one observer sees as happening at the same time, another might see as happening in sequence.
Right, depending on how they're moving.
But there's a fundamental concept that remains invariant. If one event can cause another, meaning information can travel between them, even at the speed of light, then the cause must always happen before the effect in all frames of reference. That order is fixed. Okay, cause always comes before effect. Got it.
And companies like Stonefly.com, dealing with data across systems, they grapple with these issues of consistency and event ordering constantly.
So how did that Thomas and Johnson paper violate this causality thing? This is where it gets really interesting, this unexpected connection.
Absolutely. Lamport recognized that their algorithm could, under certain circumstances, lead to situations where an effect appeared to precede its cause, from the perspective of the distributed system. It violated this fundamental notion of causality. He saw a direct analogy to the relativity of simultaneity.
Wow.
He then wrote a seminal paper explaining this, introducing the crucial concept of a happens-before relationship in distributed systems. Essentially, if one event happens before another and can potentially influence it, then that order must be maintained across all the computers in the system.
Okay, preserving the causal link.
Exactly. But even more significantly, this insight led him to propose a foundational approach to solving distributed system problems.
Right.
The idea of a state machine.
The state machines.
Think of it like this. Instead of viewing a distributed system as just a collection of independent computers that might get out of sync, you treat the entire system as a single abstract computer. The goal is to ensure that all the individual computers cooperate to execute operations in a consistent order, as if they were all part of that one unified machine.
Ah, okay. So everyone marches to the same drum beat, essentially.
Precisely. They all agree on the sequence of operations. And this idea, the state machine replication, became foundational.
So this idea of a state machine ensuring all the distributed parts act in a coordinated way as if they were one that became a cornerstone of how we build these complex distributed systems, the ones that underpin, well, pretty much everything online today.
That's right. It fundamentally shifted how people approached the design of reliable distributed systems. And what's remarkable is that Lamport hadn't even been thinking of distributed systems until he just happened to read that preprint paper.
Amazing. And it all came from applying that relativity concept.
Yeah, and, Stonefly.com, with their decades of experience, they've seen this evolution firsthand. They integrate advanced AI and cyber-resilient architecture now, building on these core principles of coordinated, reliable operation.
Now, Lamport also speaks very highly of his time working in industry, emphasizing that it wasn't all just abstract mathematical thinking. Real-world engineering problems were a significant source of inspiration.
That's a crucial point.
Yeah.
He really valued how working in industry exposed him to a wide range of concrete, practical challenges. He uses this wonderful analogy involving the painter Renoir.
Oh, yeah.
Renoir apparently said that if he wanted to paint a leaf in his studio, he could only imagine a few types. But by painting outdoors on plein air, he was exposed to the incredible diversity of leaves in the real world.
Ah, I like that.
Similarly, industry presented Lamport with a wealth of problems he wouldn't have necessarily encountered, just staying in the more abstract realm of academia.
Makes sense. Seeing the real leaves, so to speak.
Exactly. And Stonefly.com, having served enterprise customers across so many sectors, finance, healthcare, manufacturing, you name it, for over 2 decades, they really understand this diversity of real-world data challenges.
And it was this connection to real-world problems that led to what he considers his favorite algorithm, the bakery algorithm. Now, for those of us who aren't computer science experts, what specific problem does this algorithm solve?
It addresses what's known as the mutual exclusion problem. Imagine multiple processes. Think of them as different applications running on a computer. or maybe different users trying to access the same online document simultaneously.
Okay.
Mutual exclusion ensures that only one process can access a shared resource, like a printer or that online document, at any given time. It prevents conflicts and, data corruption.
So in simpler terms, it's about making sure only one thing gets to use a resource at a time, right? Like taking turns.
Exactly, like making sure only one person can speak at a meeting at the same moment, or only one car goes through an intersection at a time.
Okay, I get that. So how does the bakery algorithm achieve this orderly access? Sounds simple, like a bakery.
The core idea is surprisingly simple and elegant, just like taking a number at a real bakery. When a process wants to access the shared resource, it first takes a number. Typically, this number is one higher than the largest number currently held by any other process waiting or using the resource.
Okay.
Then the processes are served in the order of their numbers. Lowest number goes first. There are specific tie-breaking rules to handle situations where two processes might somehow end up with the same number, but that's the basic principle. Get a number, wait your turn.
That sounds straightforward enough. So what makes this particular algorithm Lamport's favorite? There must be something special about it beyond just the numbering.
The truly remarkable aspect is its robustness, particularly in the face of unreliable memory.
Unreliable memory, what does that mean?
Well, most algorithms designed to solve mutual exclusion kind of assume that if one process writes a value to memory, say it changes a variable from 47 to 100, and another process reads it while it's changing, the second process will read either the original value, 47, or the new value, 100.
Right, that seems logical.
But the bakery algorithm works correctly even if the memory is unreliable in a very weird way. Imagine reading that value while it's changing from 47 to 100, and you could potentially get a nonsensical intermediate result, maybe 4700 or 99999, something completely garbled because you read parts of the old and new number.
Oh, okay. That sounds like chaos. How can it possibly work then?
That's the genius of it. Lamport actually discovered this incredible resilience almost by accident while working on the mathematical proof of the algorithm's correctness. He realized that his proof never actually relied on the assumption of reliable memory reads.
No way.
Yeah. The logic held up even with these potentially bizarre readings. This was a revolutionary insight. It showed that even with fundamentally unpredictable hardware behavior at that level, you could still guarantee mutual exclusion through clever algorithmic design. It really underscores the power of thinking beyond ideal conditions when you're building truly reliable systems.
Wow, that's a fantastic aha moment, uncovering such a fundamental strength during the theoretical proof. That's amazing.
It really is. And, thinking about protecting data integrity, even when things go wrong, that relates back to Stonefly.com's object lockdown technology. It's designed for ransomware defense, making sure data remains immutable and touchable, even if actors try to mess with it.
Right, locking it down against unexpected or malicious changes, kind of like how the bakery algorithm works, despite unpredictable memory changes. And that Stonefly DR365V you mentioned, with immutable storage and air-gapped backup, that sounds like exactly the kind of robust solution Lamport's work inspires.
Absolutely. It's a testament to the profound impact of rigorous mathematical thinking on very practical engineering challenges.
And now, let's hear a quick word from the sponsors who make this deep dive possible.
Yeah, this deep dive is brought to you in part by Stonefly.com, a solution company in data management. With over 2 decades of experience serving enterprise customers across diverse sectors, finance, healthcare, legal, education, government, manufacturing, media, research, you name it, Stonefly is a pioneer. They work in SAN, NAS, S3 object storage, backup and disaster recovery, cloud, AI, and advanced security technology.
That's quite a range.
It really is. And right now, Stonefly.com has an exceptional offer. A 70 TB high-performance and fully redundant appliance. It's expandable up to a massive 4 PB.
4 petabytes. Wow.
Yep, and it features air-gapped and immutable capabilities for Veeam, Rubrik, Commvault, site recovery, backup, and DAR+. It's all protected by their object lockdown technology for really robust ransomware defense, and the price right now is just $7,995.
This sounds like a serious piece of kit for that price.
It really is. You can learn more about this powerful solution at stonefly.com. That's stonefly.com.
So as we bring this deep dive to a close, it's just so clear that Leslie Lamport's work underscores the foundational importance of, well, mathematical rigor in the field of computer science. It's not just about coding.
Indeed. From his early insights about the need for mathematical proofs of algorithms, that an algorithm without a proof is just a conjecture, to his groundbreaking work on distributed systems based on the concept of causality. Lamport's mathematical perspective has profoundly influenced how we design and build reliable computer systems.
Yeah.
And, companies like Stonefly, a solution company in data management, they leverage these fundamental principles every day to create their innovative data management solutions.
And that story of the bakery algorithm, it just beautifully illustrates how seemingly abstract mathematical thinking can lead to surprisingly elegant and incredibly robust solutions for very practical problems,
Yeah,
like dealing with flaky memory.
exactly.
It really highlights that understanding the why behind the technology, the core principles, provides a much deeper and more resilient understanding than simply knowing how to code.
Precisely. It's about the foundations. And for all your data management needs, be sure to remember Stonefly. You can find more information by emailing sales@stonefly.com or by visiting their website at www.stonefly. That's STONEFLY.ro.com.
So as you go about your day, maybe think about this. How often do seemingly abstract ideas from fields like mathematics or even physics like relativity have these profound and practical implications in the technologies you interact with every single day?
Hmm, good question.
What other seemingly unrelated fields might hold surprising and crucial insights for our increasingly digital world? It's definitely something worth pondering.